They all look good. E130. It's device distance.
You just solve the whole equation. Where do you think these squared
Just
D squared is easier.
yeah, yesterday my friend.
It's just the equation is find the square over 4d squared. So you just plug the 1 over d squared in. So it's like no. Letting various values of HK. So you get to well, I think like educated HK gets it. So trying to get smallest theta. Sine squared theta equals lambda squared over 4d squared.
So wait.
Smallest theta equals small set of HK. Like 001 usually is they're not. So, because there's two tetragonals, one has A equals 2, C equals 3, and the other has A equals 3, C equals 2. So in each case, you would minimize A maximum.
It looks like this is going to be pretty simple. Because you're saying, because I'm not going to do something. Oh, yeah. So they're like, they'll just like look for people that need it now, and then like when the time comes in, yeah, they said they might have to well, kind of not like a yeah, not like an interview, like an interview with like a manager that is helping my work. So I already passed the 2 interviews. Hey, so technically I all have one more show. Just this week. Like 105. There's a part of me
Okay. All right. Good afternoon, and welcome to this review session. So, as I mentioned before, what we plan to do is two parts. Half of, or at least a little bit more than half, I would like to devote to general questions. Any particular question, say, hey, this part of the material, could you go back to that a little bit? That's kind of bizarre to me. So I'll first collect a set of questions, and then I kind of rank order them a little bit in such a way that it kind of makes logical sense, so we don't do random hopping. And then what I'm going to do is actually go to two alt midterms and give you an idea of what are the type of questions. And if you're asking yourself, what is the midterm going to look like? Well, I think the best way to do that is look at the alt midterms. It really does describe it perfectly well. So there are a whole bunch of them online. Have a look at them, kind of figure out how if you can handle those, you're going to be in good shape. I can tell you that. So that's what I definitely would recommend. So we're going to walk briefly to some of those and kind of pointing out what's the particular things that I was after, or that the person who has created the questions was after in those particular midterms. Okay? So let's first start kind of collecting questions and topics that you would like to see kind of briefly rehearsed or revisited. I'm going to write them down, and then I'll basically do some ordering based on that. Not all at the same time, okay? Yes?
Transient analysis.
Transient analysis, okay? In general, right? Or do you are a particular, is it a particular aspect?
In general.
Okay. Okay. Other topic? Good.
Regenerative property, mostly this picture.
Okay. Regenerative property. No spelling checker on this. Yes? Okay.
For one of the capacitance, it depends on whether you, I don't know, it depends on whether you're in triode or saturation. Can we just assume that the 2/3 is always 1, or should we always?
Okay, capacitance. Let me go a little bit to this capacitance and what to assume. What to assume. I'm going to go briefly to that. Okay? That's it? Wow, you guys are smart. Yes?
When you put a step input function into
Right.
an inverter, why does it make that spike in the beginning?
Okay. Step, let me just call it feed through. Okay, I'll give you the answer right away, but okay. Any other particular topics? That's yes.
When you're linearizing the capacitors,
Mhm.
you have the factor K equivalent,
Mhm.
and selecting the V output high, V output low, and the output high, what values you get.
Okay, very good. How to pick the range? Okay. There was another question somewhere. Mm-hmm.
The gate capacitance, why it drops down and then comes back up.
Okay, so it seems like we have a nice set of questions about capacitance. So I'm going to definitely go to capacitance a little bit. Any other questions for the time being? Think about it. I might start, and if there's some other things that pop up in your mind, we definitely can add those if time permits, obviously. So I have 1, 2, 3 questions on capacitance. I have 1 question on transient analysis. This is also transient, feed-through effect. So let's briefly start with regenerative, kind of the order, and then I'm going to go a little bit into transient analysis, some of the effects, and we're going to talk about capacitances. Right? That's kind of where the way I would like to structure it a bit. So let's think first about the regenerative property. What it's all about. So it's an important property of a digital gate. Let's say, suppose that I would have I would implement logic using just switches. Just an example, right? I can have, let's say, a network, and I put some in parallel and some in series, and so on and so forth. And this is my input, and this is my output. So you have capacitors on every intermediate node. Now, if you have a logic family like that, what you see is the following thing. Suppose my input is perfectly fine at VDD. It's a nice, perfect value. But then I store this, I have the first switch, I get VDD here, but I add some noise. Some noise comes in. I have some coupling to the neighboring wire. And instead of VDD, I get VDD minus delta V. Okay, I lose some voltage. Okay, because of the noise coupling through mixing through another capacitor or something like that. But I lose some signal. Okay. Now, if I go to the next switch is not going to do anything about it. Actually, the voltage I'm going to pass is still going to be VDD minus delta V. Now, suppose I go further in the chain, I have another noise source, which again basically moves that value around. Maybe I get now VDD minus delta V prime, which is larger. I lose even more signal. And so on and so forth. You see that in a network like this, you never recuperate from anything that happens that's bad in the chain. Right? This is an example of a non-regenerative network. Noise comes in and it accumulates. And the deeper you go, the more noise, and suddenly you might not be able to figure out if it's a 1 or a 0 anymore. Okay? So that's an example of a non-regenerative network. It's clearly something that's not scalable. You cannot make very complex networks that way. So that's why we would like to see our digital gates have this regenerative property. The idea of the regenerative property is that if I take a gate, I'm not saying exactly how it's implemented, but I apply here, let's say, suppose I have two inverters, just to make life a little bit easier. Suppose I apply here VDD minus delta V. Okay? So the input signal here is not perfectly 1 or a 0. There's some noise added to it. A logic gate that has a regenerative property has the property that while you progress to consecutive gates, actually the impact of that noise is going to disappear. And if you go to enough gates, we're going to be perfectly back at VDD or at ground. So the noise, impact of the noise gradually disappears while we're going through consecutive gates. That's a good property because now it means that I can build very complex networks and I inject some noise at some place. It kind of gets smaller when I go to consecutive steps. Now, what do we need to have to make a gate to be regenerative? Okay. Well, there's one key property. The key property is that the voltage transfer characteristic of the gate has to have a property which looks like this. So this is V out, this is Vi. What we really need is a transient region with a gain larger than -1, absolute value. Okay, so we have to have the gain we have to have some substantial gain in the intermediate region. Because what's going to happen if you go to consecutive gates, and you can actually show this quite nicely. The way to plot this is by let's say, the voltage transfer current. This is say I have a sequence of inverters. So suppose now that I apply an input here which ends up somewhere here. It's not a perfect, normally we would like to see the input to be perfectly 0, but there was some noise added which was delta V. Okay? So you can see that the output of this gate is not going to be perfect. But what you observe is that because of the fact I have gain here, is that while I have delta V here, delta V prime at the output is going to be smaller. Because of the fact that in this intermediate region, I have a gain which is larger than -1. So you have a certain deviation, and the deviation at the next gate is smaller. And if I apply this to the next gate, which I can now do like this, because now this is the input of this V out is the input of the next gate, and this is going to be Vi2. So this is Vi, this is Vo, this is Vi2. The output of one gate is the input of the next one. If I now apply this input signal to this structure right away, we see that the output is going to be perfectly back at 0. Right? So bottom line is the noise has totally disappeared. And you can easily show that the more gain I get into transient region, the steeper the transfer characteristic, the better the regeneration is going to be. Okay? So that's the whole idea, is that if you have a gate which has transient gain, or gain in the transient region, here in the transition region, if you have gain which is larger than 1, you will see that noise will disappear. This network has no gain whatsoever. Right? There's no gain factors in here. You just pass the signal along, and everything you add up basically is additive. It gets worse and worse and worse and worse and worse. Okay? So that's the whole idea of regeneration. Not all logic families have this. Like, for instance, we'll show you that if you have dynamic logic, I think I briefly mentioned the last lecture yesterday. If you have dynamic logic, under certain circumstances, you're not going to be regenerative. You have to be careful. You actually can have noise being added that doesn't go away. So you have to be very careful in those logic families when you deal with noise, or when noise happens. You have to make sure you don't have noise whatsoever. Question?
I think we've seen 3 different types of inverters, the CMOS and then 2 different NMOS inverters.
Mm-hmm.
Is the CMOS the only one that's regenerative?
So that's a good question. So we showed you during homework, something like that. We showed you some other inverters, like the one that we call the saturated load inverter. That's one example, where you use an NMOS as a load, and this is the output, this is the input. If you look at the voltage transfer characteristic of this one here, it's not as good. It's going to be a kind of an iffy thing. It's going to be like this, right? That's what you kind of get. But you still see that I have a very nice region here of regeneration of gain. So this gate is regenerative. I'm not sure what other NMOS gates you've seen, but for instance, if I would have something which has a resistor, again, that is a regenerative gate because it will have gain in the transition region. So these are all regenerative gates. The only example so far that I've shown that I would use pure transistor switches with no connection to VDD and ground in between, just at the input, this definitely is not regenerative. Okay? Good. Does that answer the question on regeneration? Okay, so let's go to the second topic, which was a bit about transient analysis. Okay?
Question.
Yes.
In previous sketch, even the input signal is above the VIL.
Mm-hmm.
It can be regenerated too.
It will be regenerative, yes. Even if you go in the transient region, here, the problem here, obviously, I don't really know if it's going to be a 1 or a 0. It's kind of indeterminate. But if you go to enough gates, it's going to be for sure going back to the 1 or 0 regions, which is guaranteed. That's something I can recognize. So even if I drive it away into something which is undefined, it still ultimately will go to one side or the other side, and you will have deterministic signal. Okay?
So undefined only for several stages.
That's
but
right.
Finally, it will
Yes,
be defined.
but it's fast, right? If you have a gain like 10 or 100, something like that, you will actually, CMOS inverters have a gain of what? Approximately 15. That typical number, 10 to 20, is the range of a gate of a normal CMOS inverter. You do that, you will see that you can have a sizable disruption. In about 2 invertive stages, it's going to be gone. It's really quick. But it depends upon the gain. If I have a 200, let's say, if I make a gate which runs at 100 millivolt supply voltage in a sub-threshold or something like that, you will see there your gain is a lot smaller. You end up with something that looks like this. That's your gate approximately. There it might take a lot more stages to really get back to. But as long as it's larger than 1, this is 1. It depends what that's how my axis look like. This is approximately 1. This is on the edge. This thing will barely function. Okay? And will basically accumulate noise. All right. So let's talk about transient analysis. Okay, so the whole idea of so what we have is somewhere a transistor set network driving a capacitor. Right? So all the transient analysis, propagation delay analysis is always what we're gonna do is take our capacitors, which can come from many sources. We'll talk about that later. We linearize them and we lump them together into one load capacitance. That makes life easier. Rather than having a very complex network with a lot of resistors and capacitors, now we would like to have a network with one resistor, one capacitor, or one current source and one capacitor. So and then you have your driving gate, which let's look at a CMOS inverter. Okay. So this is my input, this is my output. So I ask you to compute the propagation delay of a network like this. Two basic ways of attacking it. And both of them are valid. They give you approximately within 1% the same answer. But both of them are approximations. So what I said is already, I linearized the capacitance and I lumped it. The transistors, however, are also nonlinear elements. Right? They go to different operation modes. And as a result of that, the current characteristic can change as a function of V in. So these are all nonlinear. So what we're typically going to try to do is replace this by a linear element that if you would put the two curves together, so you have your real curve, you look at and you apply an input, let's say, which is a step. And at the output, I get something which is going to respond a certain time later. We're going to replace this by a new element. This is the ideal, that's what SPICE would give me. We're going to replace my transistor by a linear element, which might be a little bit different in its curve. But in the 50% point, you get exactly the same value. Which is okay. I don't really care about what's happening in between. What I really care about is what's my propagation delay. So if I get a way of approximating that gate delay in the perfect way, I'm going to be in good shape. Okay? So that's what we're trying to do. Now, two ways, and both, as I said, both of them are equally valid. And it's up to you to judge a little bit what's the easier way. Remember, like always in life, the easier way, probably also very often the better way. You can make things very hard and very complicated, or you can make them easy. And obviously, I typically choose for the second one. So two options, as I said. So let's look at the high to low transition. Okay, high to low transition means my output is high initially, the PMOS is on, the NMOS is off, and then I apply a step at the input. PMOS turns off instantaneously because it's step, so the VGS of the PMOS goes to 0, the thing turns off, and the NMOS turns on, and we're going to start discharging this capacitor. So what we know about the NMOS here, about this device, is that VGS of this device is going to be constant during the whole transition time. It's going to be equal to VDD. Right? Basically, the VGS goes in one shot from 0 to VDD and stays at that value. If I look at the current that's going to flow to this device, if I have my NMOS characteristic, we know you get something like this. That's your NMOS ID versus VDS for different values of VGS. Right? Well, the curve we're going to pick, as I said, VGS is a constant. It's equal to VDD. It means that the whole transition is going to happen on this curve here. Because VGS, the curve where VGS is equal to VDD. Okay? So we're going to start here, but because we start with VDS equal to VDD, that's the first point. And then we start discharging. The voltage is going to go down and down and down and down until it gets 0. But the characteristic, the current, is always going to stay on this curve. Because, as I said, VGS is constant and is equal to VDD. Now, what do I care about? Again, this is kind of a nasty curve, right? It's a nonlinear curve. However, remember the propagation delay definition? I don't really care about this part at all. Because the propagation delay is defined between the point where we start at VDD and the midpoint of our transition. VDD over 2. Or VOH minus VOL over 2. But in this case, that's VDD over 2. So the propagation delay, the end of the propagation delay analysis is when VDS becomes equal to VDD over 2. Okay? So we see that in this period of time, the current through the transistor is going to be almost constant. Right? This looks like it's a saturated, velocity-saturated device, so the current is constant. Now, a device where the current is constant is called what? That's called a current source. So a good approximation of the transistor during this period of time would be to replace the transistor with a current source that's discharging this capacitance CL. Okay? I. Now, life would be really beautiful if the current would be really flat during this period of time. Then I don't even have to worry, but current is always going to be constant and it's going to be exactly equal to this I. In reality, there's some channel length modulation effect. Right? Actually, you see this curve goes upwards a bit. So the question is, what do I use for I? I want to linearize the I want to replace it by one constant current over the whole interval of interest. A couple of options, but here's the simplest one. At this point in time, I have a current called I1, which I can compute. If I, let's say, assume that we don't have velocity saturation, this would be equal to KNW over L times VDD minus VT squared times 1 plus lambda VDD. Right? Because the VDS at that point in time is equal to VDD. That's my equation of the current in this point. As I said, I'm assuming it's not a solid velocity saturated device for simplicity. The value I2 we can compute as well. It's the same equation, we're still saturated, so we get I2 is equal to Kn W over L VDD minus VT squared. That doesn't change, VGS is still the same, but we get 1 plus lambda over VDD over 2, because VDS has dropped over to VDD over 2. And that's the difference between those two currents here, is this factor. Okay? So we know the two values at the extreme points. So a very simple way to approximate this thing is, say, well, why not replace it by one single current, which is the average of the two. So I say I is going to be equal to I1 plus I2 divided by 2. And I put this in my current source. And that's the constant current that I have. So I compute the current, and then you have your equation here. You know that TP is going to be equal to CL times VDD over 2, 50% point, divided by this I value, which is equal to I1 plus I2 over 2. Okay? There's better ways. I can take the average of the two. That basically says I'm going to replace it by a constant current, which is the average. I could also use integration over that period. If this curve would be a little bit more complex, actually. But actually, if this is a straight curve, the average is just fine. It's just as good as it gets. Yes, question?
When can we assume that we ignore velocity saturation?
I will tell you that.
Oh, like in the question.
In the question, I will tell you. Typically, obviously, in real life, it's your job to figure that out, right? If you do a real design with a certain technology, if I basically use a 65 nanometer transistor, and I have a voltage that runs around a volt, I know I'm going to be velocity saturated. I have to assume that. But in the exam, I will tell you very explicitly, long channel device, short channel device, this is what you should consider. Yes?
So if we calculate delay as the difference, I might be sorry, the difference between 50% plus.
That's correct, yeah.
So then why can't we just take the current at VDD over 2? Because isn't that what we're talking about?
No, not really, right? It's a transient. So what we're doing is we start in discharging capacitance. Initially, actually, we're going to start with this current. You start your transition, you start with this current, and you start taking charge away. You can imagine if I would have a curve which looks like this, you see that this current is going to be a lot more effective than this current. So you better make sure this one is doing a lot of work, while the one in the middle is kind of already becoming slower and slower. So now you have to look at the current. You're looking really at the charge, right? I have a certain amount of charge that I want to remove. And that charge is going to be, and the current basically helps me to remove that charge, right? So that's why you have to look at the whole interval, not just at the midpoint. It's a transient. It's not a DC characteristic. Okay? So that's approach number one. Yes? This one here? Oh, this one here? So if I take a, let's kind of look at, you have a capacitor, which you discharge with a constant current. Okay? That's what we're doing. It's a constant current. You know that if you do so, the voltage is going to look like this. You start at VDD, and you will get a linear reduction of the voltage. Right? If I have a constant current discharging a capacitor, that's what I'm going to get. Yes?
For the top, do you just assume since VGS, since the input's VDD, that the top is just off, so it's just like an open circuit?
Yes.
Okay.
Yes, because remember, we have a step function. The PMOS goes off instantaneously.
Okay.
Unless, obviously, there would be some leakage going on. But for the propagation delay, the leak, in definitely typical design, your leakage current is going to be small compared to the discharge current. And the impact on propagation delay is going to be small. It has a much bigger impact on power dissipation. But in terms of propagation delay, leakage doesn't matter that much. Okay? So that's really what we're doing. We're discharging a capacitor using a constant current source. So now think about it. Tp times I is a certain period of time. This is Tp. Okay? That's the time where I start here, and this is where I'm reaching that midpoint. So this is VDD. This is VDD over 2. Right? That's, and this is time. So Tp times I, what units give that? That's charge. Right? If I multiply current by time, I get charge. So a constant current source in a period of time Tp will remove a amount of charge which is equal to Q, which is equal to this value. Now, how much charge do I remove? Well, the charge that I basically have stored on the capacitor was initially CL times VDD, but I go to the midpoint, so the amount of charge I'm removing is CL times VDD over 2. So this is a charge on the capacitor that I'm removing. This is the removing source. And obviously, they have to be equal to each other. So that's why we get Tp equals CL times VDD over 2 times basically I. Okay? So that's one particular equation that I could use. And as I said, sometimes it's very easy. If the current is approximately constant, this thing is easily computed, right? You take the first value at this point, you take the second value in the midpoint, I take the average of the two, and I'm done. Okay? Now we have approach number 2. And it also has its value. Which says, gee, current sources are nice, but if you look at interconnect wires typically are resistive capacitive networks. If I start chaining gates together, current sources and things don't mix very nicely. Wouldn't it be nicer if I can basically express everything in terms of resistors and capacitors? No current sources. Right? So I can build an equivalent network of my logic only consisted of resistors and capacitors. And I'm going to use that to evaluate my propagation delay. That's easy to do. We know how to solve RC networks, at least approximately. So that's the second approach. Well, now, instead of assuming that I'm going to use a linear current source, I'm going to replace my transistor with a linearized resistor, R equivalent. Okay? And this is, again, CL. Now, in that for that circuit, we can compute the propagation delay quite rapidly. Tp is going to be equal to ln2 times R equivalent times CL. And this ln2 is 0.69. That's a standard circuit. It's an RC network, first order RC network. We know that the propagation delay of a standardized RC network is your time constant of your network, R equivalent times CL, times is 0.69. Okay? So that's easy to compute. The equation is a little bit easier than this one here. The challenge, however, is to figure out what is R equivalent is. What is the equivalent resistance of my transistor? Again, let's look at our current characteristics. So we get I, and we get VDS. And the same curve is still valid. All right, we start at this point, and this is the midpoint where we get VDD over 2. And this is equal to VDD right here. Okay? But now, instead of replacing this by a current, we would like to find an equivalent resistance. Now, what is the definition of resistance? It's voltage over current. Right? At any point in time, if I want to replace a circuit by a logic element by a resistor, I measure the voltage, I measure the current, divide the two, and I get the equivalent resistance. Okay? So what's the resistance in the begin point? Well, the resistance in the begin point is going to be equal to this current here. Let's call this I1, and this is I2. Okay, like we did before. So R1, the first resistance, is going to be equal to VDD, that's the voltage over my element, divided by I1. Okay? That's R1. This resistance in this point is really the angle that I see here. This angle, VDD over I, is an angle, right? So this angle is a measure of the resistance at that point in time. So it's VDD over I1. In the midpoint, we have a different resistance. The resistance has actually gone down. It's going to be equal to R1, R2 is going to be equal to VDD over 2 divided by I2. Right? Which is the current in this point. So I have two resistances. And now the question is, what's going to be, I would like to replace this by one resistance. Well, we're going to do the same thing like we did with the current. We say R equivalent is going to be R1 plus R2 divided by 2. That's one way of doing it. I could also, again, I could integrate it over the whole interval, and this way find the average. But it's a very simple way of finding the average. Is you take the two extreme points and take the average between the two. Okay? Now think about what I get in this case. So this R equivalent is R1 plus R2 divided by 2. It's going to be VDD over I1 plus VDD over 2 times I2 is equal to, those things are quite similar with respect to each other. So I can take VDD over I1, and you get here 1 plus 1/2 over I2 over I1. Plug in the equations, and you do the whole analysis, you will see that actually you get an equation which is pretty close which I will get from here. They're not that different. Right, so I have the R equivalent, I multiply this with CL, and you take this, and you compare this, and you multiply this with 0.69, and you take this equation here, and you see they're very close. They're not going to be perfectly the same, because we took it's a different way of averaging that we're doing. So as a result of that, there will be a small difference. But both of them are equally valid. Both of them are reasonable approaches. This is a little bit more kind of questionable because this clearly doesn't look like a resistor to me. Looks like a current source to me. So the resistive approximation kind of makes some, is a little bit more contrived. But as I said, the advantage of this approach is that if I now connect a wire to this, which has a resistance, I just keep on adding the wire. And if I have some more logic circuits loading it, I can have more capacitance connect to it. The whole thing becomes a large RC network. And those things are easy to evaluate. Okay? That's why we typically like, that's why I like the resistive equivalent. But in certain circumstances, you look at your problem and say, hey, I know how to compute I1 and I2 very easily. I can see it. Use this way. It's a lot easier. So pick the thing that you think is going to be the easiest for you. Okay? So that's your propagation delay in general, and you can go the opposite way as well, right? You can go, yes?
On the other diagram, the way you did it the first time, you had the Q equals I TP. And then you said that equals CL VDD over 2.
Here? This one here?
Yeah, and then you were explaining it further.
Yeah.
And you said Q equals I TP.
Yeah, Q is equal, oh, you had it somewhere here. Yeah. So this is the charge that I'm going to remove by, if I take a certain time TP, with the current source, I take a certain charge Q that I'm going to displace, right? And that charge is going to come from the capacitor. Now, during that propagation delay, the definition of the propagation, you go from VDD to VDD over 2. So the amount of charge I remove during that period of time is CL VDD over 2. Right? I go from VDD and I go to VDD over 2. So that's the amount of charge, CL VDD over 2. Those two have to be equal to each other. And that's why I get TP is CL VDD over 2 divided by I. I take I, divide it out here, and we're done. Okay? Yes?
So you had like the resistive network with like an R and then a C going to ground and then another R and then a C going to ground. Calculate the TP for that one again.
Good question. I'm not going to answer you right now on purpose. Well, you can do it. There's a couple of ways. In home number 2, or you actually we gave you a glimpse of it. There's option number 1 is I write down all the equations, Kirchhoff's law. You can all those things. You write down the equations and you get something which becomes quite complex. Actually, if I have multiple R's and multiple C's in a network, in general we get a higher order network, which means that it's described by an nth order differential equation. Right? So I can write down the differential equation, then solve the nth order differential equation. And it's going to give you a nice answer, and it's going to be the right answer. But there's one problem with it. Nth order differential equations is not something you kind of do for breakfast. It's something that basically takes some time and some effort. However, there's some beauty to it. The fact is that we'll show later, when we talk about wires we typically will model as networks like this. Go with your resistors and capacitors in series. That actually, there's a fairly simple way for me to estimate the first order moment, as they call it, or actually something which is very close to what we call the time constant of this network, a dominant time constant of this network, which can help me to predict the propagation delay without having to go to this very complex differential equation kind of story. So if you would see something like that on the midterm right now, there's not much choice. Write down the equations, write them all out, and solve the differential equation. Good luck. So clearly I'm going to stay a little bit away from that. I'm not going to ask you right now to solve nth order differential equations in the midterm. You have only an hour and a half after all, right? But later on we're going to show techniques, which is called the Elmore delay expression. Just remember the name for the time being. We'll come back to that later. Something that allows us to take a fairly complex RC network and say, hey, that's the delay of that network, without having to understand all the intricate details of how the waveform kind of changes. Okay? You heard what I said, I think, so it should be pretty clear. Okay? So that's the transient. There was one question of why, if we do SPICE simulation, you take an inverter and I apply a step. Doesn't even have to be a step. Something that goes quite steep from high to low. If you look at the output, what you would expect, obviously, is something like this, right? You would expect that you start at VDD, this is T, and something you're going to go, and you go down to 0 over time. That's the waveform you would like to see. So you start discharging, the NMOS starts discharging your capacitor, and it should go nicely and monotonically to 0. Now you put this in SPICE, what do you get? You get something like this. right? So why is that? Why do I get this hump here? What's the reason for that? Well, this is something we call feed-through. And it has directly to do with something we discussed when I'm going to discuss it in a minute when we talk about capacitors. If you think about the capacitances of this gate, well, there's the capacitors to ground at the output here, which are your diffusion capacitors. This input node will see some capacitor to ground, which are your gate to source capacitances. But remember, there's also a capacitance that sits between the gate and the drain of our transistors, the gate to drain capacitance. Now think what's happening. So I apply a steep function here. The PMOS doesn't turn, is turning off, the NMOS turns on. But you see that initially, so what we get is a network almost like this. You have a capacitive coupling, we have another capacitor here, and we have a resistor. Right, that's CL, this is CGD, and that's my input. Right, so you would expect normally, bingo, you are going to have this very nice propagation, you're going to discharge your capacitor, and bingo, you're going to be nicely done. However, this capacitor plays as well. This is a capacity divider, right? Two capacitors. If I now apply a step here, this is at VDD. This node initially at 0 goes in one step from 0 to VDD. Right? You can see capacitive coupling is an instantaneous thing. Right? You have two capacitors in series, and I apply one voltage, and the other guy is going to follow right away. So this is going to push, I move this node up, this node is going to try to follow. Not as directly, but it's going to be a divider sitting in between those two steps here. So what we're going to see is that the input is going to couple temporarily to the output. It's going to go up. If you wouldn't have this resistor here, it would stay there actually. However, then the resistance comes in action and says, okay, I'm going to start taking the charge away. So that's why we first shoot up and then we go down. It's because of this capacitive coupling between the input and the output. And that's why you apply that step propagates directly to the output in a attenuated fashion, obviously. Not directly at the same level, attenuated, but you see it happening. Feed-through is an annoying factor because you can imagine. Now you might ask yourself, how big can this be? How can this delta V be? And how big should it be? Well, it's kind of scary to have these big bumps up there. Why? Well, remember our transistor. So this is a PMOS device. Okay, so we have P plus here. And we have P plus here. You have an N well, and you have. So this thing sits at VDD, and this is my output, and this is my gate. Okay, so this gate is taking this big step, right? And now you have this capacitive coupling between here and here. This shoots upwards. Remember the well, in this case, this N material is going to be at what voltage? There's a P well, an N well, sorry. It's going to be at VDD, right? Now, what's happening if I now start raising this output voltage above VDD? This diode is here, right? There's this diode which typically is reverse biased. Right? It's definitely not on. But if this voltage here, V out, is going more than one diode voltage, 0.6 volts above the rail, this diode turns on. And I start injecting current directly from my drain into the substrate. And this can have some nasty effects. I mentioned this, I think, last lecture or 2 lectures ago, something which is called latch up. I'm throwing charge around in the substrate. We don't like that very much because there's some weird devices hitting in here. I already mentioned there's a PNP in here. But actually, you put an NMOS next to it, you could have a PNPN. And PNPNs is something that power device guys like a lot. It's called a thyristor. And one thing about the thyristor is once you turn it off, there's no way you can turn it off anymore. So what's going to happen is once this thing goes on, you might see your current flowing. This thing's go, and it keeps on going, and it keeps on going, and it keeps on going. Huge amount of current flowing to your substrate. And suddenly you see some smoke kind of whirling up from your chip, and the story is over. You better get a new chip. Okay? So that's why this is kind of worrisome, that overshoot. If your feed-through capacitor is large compared to your load capacitance, you have to worry. But most of the time, your load capacitance is going to be much bigger, right? You have all this fan-out, fusion capacitor, wiring capacitance, connected gate capacitance. All those things are sitting there. And that this thing is almost nothing else than overlap capacitance. So the ratio is going to be small. So the little hop is going to be quite small. The reason why you see it in SPICE is because of the fact that you didn't make your CL big enough. If you make your CL big enough, you won't see this effect. It gets a lot smaller, and you maybe get 50 millivolts or 100 millivolts or something like that. But that's not bad, as long as it's not 600 millivolts. When you get to 600 millivolts, you run in trouble. Okay? Clear? So that's the effect of feed-through. Okay, so now let's talk a little bit about capacitance. There was a set of questions about capacitance. A lot of things to be said about it, but let me first look at the gate cap. Right? The gate cap and why it does these weird thingies that we have observed. So again, let's try to draw out my transistor. I have N plus P and a gate. Okay. So let's assume that there's no overlap capacitance for the time being. I'm going to ignore that. Okay. You know that all the time, in reality, you're never going to get this ideal situation. What's happening while we're processing the chip, while we put the chip through some high temperature steps, we put it in the oven, we put it at about 600, 700 degrees Fahrenheit or Celsius. Every time you heat up material, diffusion happens. Right? So even though I might create a perfect implant, so the way you create the source and the drain is implanting impurities, and you use the gate as the kind of the blocking material. So this is why we get perfect N plus here, and we don't get N plus here at all, because the gate basically captures all those particles that I'm shooting at it. So it only ups here. So this is called self-alignment. It's a beautiful concept, right? You put the gate down over the silicon dioxide, and then you shoot all those ions at it with a huge amount of force. So they end up here, and you have all those impurities. And the gate, basically, we have this polysilicon. The polysilicon is just going to take those things, and they're going to go into the polysilicon. And as a result of that, you get a perfect edge between your source and your channel and your drain and your channel, ideally. But then I start cooking again. I put the thing in the oven, and what's happening is these N plus parts start to diffuse, like they always like to do. There's a P here, there's N here, you heat it up, the impurities start to move to areas where there's less of them. So that's what causes the overlap capacitance. The under diffusion is that this region extends a bit underneath the gate. Okay? And that's what your overlap capacitance is. This overlap region is totally worthless. Right? From a transistor perspective, it doesn't do any good for us. It destroys the channel. It removes the channel. So now instead of having an L, which is initially this big, we end up with an L which is equal to L effective, which is smaller. The actual channel length is going to be smaller because of the fact that we have this under diffusion. Okay? And at the same time, we're going to have some fixed capacitance between the gate and the source and the gate and the drain, which are due to this overlap capacitance. Okay? That's fixed. That's a linear capacitance. Right? It's really silicon dioxide. And you have on one side, you have your drain, and the other side, you have your gate. It's a parallel plate capacitance as good as it gets. So I'm not going to talk about that anymore. That's always there. But let's think about the channel capacitance, okay? The other part of the capacitance. So let me now go back here. Let's redraw this again. So you have N plus, and the gate. Source and drain. Okay, so what's going to happen with the capacitor here? The total capacitance I'm going to see here from the gate is equal to W times L effective times C aux. L effective is now the actual channel length that I see here. Okay, that's the total capacitance. It's parallel plate capacitance. That's what I see. WLC aux. Now the question is, where does it go? So we know from looking into this gate here, we see this total capacitance here, WL effective C aux. Now the question is that a capacitance to source? Is that a capacitance to drain? Or is it capacitance to bulk? We also have our bulk contact here. And the answer is we don't know. It varies. It changes. It varies depending upon the operational mode of the transistor. So think about it. When the transistor is really hard off, I basically apply here I put these things to ground, and I apply a gate voltage which is very negative. I really turn it off hard. Okay? What you're going to see is that in this case we'll have the capacitance I'm going to see as a function of VGS. This is C gate is going to be equal to this WL times C aux. The source and the drain are off. They're not into the game at all. So all this capacitance, I apply this here, is directly a capacitor that connects to the bulk. Okay? Now, remember what's happening when I start now increasing VG. I start increasing the gate voltage. What's happening underneath that gate oxide? What's happening at the surface here? I'm starting to push away holes, right? The holes, this is a material which is P material, so I have some free running holes in this. I start to push them away. I create a depletion region underneath the gate. Now this depletion region, remember about diodes, if you remember something about diodes, you know, depletion regions has capacitance connected to it. It's like a capacitor. So what we have now is a capacitor first that's equal to the capacitance of the gate, the WL times C aux. But in series with it, we have a second capacitor, which is the depletion capacitance. So my gate to bulk capacitance is going to be equal to C aux plus C depletion. Okay? Sorry. I'm wrong here. It's C aux in series with C depletion. So it's not a sum. Actually, it's a parallel. It's a series connection. So it's Cx times C depletion divided by C aux plus C depletion. Right? Remember capacitance in series. It's like resistors in parallel. So it's C aux times C depletion times C aux plus C depletion. Now the net effect of this is that you can look at it, it almost becomes like a broader, wider and wider capacitance, right? And you remember a wider capacitance that basically gets thicker and thicker in terms of insulation material, it's a smaller capacitance, right? The capacitance is always proportional to epsilon over T. If T gets larger, the capacitance goes down. So initially this is constant, and then we will see my capacitance starting to drop. Okay? So that's why you have this dip. A depletion capacitance forms. And then suddenly, click, you basically, the voltage at the surface is going to go to 2 phi F, which is the Fermi voltage. At that point in time, suddenly we get strong inversion on the channel. Suddenly we get this material basically, instead of becoming P material, becomes N material. It inverts. And a channel forms with free electrons. Channel is a conductive medium. It has free electrons. It can basically conduct. It acts actually from that point on, this whole bulk is shielded away from the gate. The gate doesn't see the bulk anymore because you have a conducting layer underneath your capacitor. So what's happening once you reach the threshold voltage of the device, suddenly, bingo, your capacitance is going to jump back up. The depletion capacitance disappears on me. But now the difference is that this capacitor is not going to go to bulk anymore, but it's going to be equally divided between the drain and the source, because you have this conductor sitting underneath the channel that connects the other plate of the capacitor to both the source and the drain. And it kind of equally divided between the two. Okay? So, yes?
Why does it go back up to WLCL?
Well, that's the only thing I have left. So we look at the capacitance now between the channel and the gate is WL times Cox. The depletion cap is gone. It's gone to, we don't worry about this anymore. We're back to the Cox value.
Well, if it's a conductor, it's like a capacitor with zero capacitance, isn't it?
No, so you have the gate here. You have silicon dioxide. And I have my channel. The channel, so what I have now is a capacitor that has on one side polysilicon conductor, on the other side the channel as a conductor, and in between a dielectric material with a thickness equal to Tox. So the capacitance here that I see is epsilon ox over Tox times W times L. So that's why that's the only capacitance I still see. Okay? Now that's for linear mode. When you go to saturation, the story is a little bit different. Because now this channel gets punched off. So I start raising VD, and at some point in time, we don't have a threshold voltage between the gate and the channel anymore. So we don't have strong inversion at this end of the channel. So you can look at this as having now a conductor that basically extends partially underneath the channel. And then some other capacitance that goes places. Now, places, this is, obviously it's not abrupt. This is the extreme case. When you go from linear to saturation, how the capacitance is going to go between source and drain is gradually going to change. It starts with both half at source and half on the drain. And gradually but surely, more and more of the capacitance will appear at the source. But it maxes out at 2/3 times WL times Cox. And you can ask me, where's the other third? Where did that go? And that's a good question. It's something, if you actually work out the equation, you see it's perfectly legit, it's perfectly correct. But it's not something which is something you can explain intuitively. You really have to work to the analysis of the capacitors, work out the charges in the channel, integrate them out, and you basically will figure out that the 2/3 actually is the right answer. So there's no capacitance anymore to drain at that point in time when you go into saturation. Okay? So now there was a question about what should I assume? Again, depends on how I phrase the question. In general, you may assume that if I say, well, gee, you have to make sure that you take all the nonlinear effects into account, then obviously you have to figure out if the transistor is in saturation mode, it's in linear mode, and you use the right values. If I say, no, you can actually simplify the thing. Let's assume that the gate capacity is C times WL times Cox. You're fine. Right? So I'm going to once again make it explicit for you. Okay? All right, that's gate cap. There's one more question that I had regarding capacitance. It's up. The last question is about the diffusion capacitance. The diffusion capacitance, remember, is the capacitance that I get N plus P. We have those reverse biased diodes sitting right here. Sorry, like this. I have another diode like here. So diodes come with capacitance, depletion capacitance. Actually, it's pure depletion cap. Very nonlinear, and we know the diode capacitance looks like something like this. If this is the voltage over the diode, and this is the capacitance. This is the voltage when the capacitance when you have 0 voltage over the capacitance. You can see that if you go more and more reverse biased, that the capacitance gets smaller. you get a thinner and thinner depletion layer. While if you go on the other direction, basically the capacitance actually goes up quite. No, sorry, it gets thinner and thinner here. Here you get a thicker and thicker depletion layer. That's why the capacitance goes smaller. So you have very heavily reverse bias, very small capacitance, but then you go forward bias and you see that the capacitance actually goes up substantially. Very nonlinear. So as we said, what we're going to do is say, well, gee, that's a pain in the butt. Again, you have a capacitance that varies quite substantially with the data value. Very hard for me to do analysis for my propagation delay. So what I'd like to do is replace it by a capacitance that gives you the same charge displacement as the nonlinear capacitance does between over the interval of my propagation delay analysis, like before. So let's look at two cases. Okay, so let's consider first high to low transition. Okay, what should be, so you have the equation, it's in the book, you have it, you should know about that. So you have this equation that allows you to express that linearized capacitance and compute this K equivalent factor. Right? It says C equivalent is equal to K equivalent times Cj0, and Cj0 is the capacitance for Vd equal to 0. Okay? So that's what we want to do. It says the question now is what values of the voltages should I plug into my K equivalent? And the answer here is it really depends upon what transition you're considering. Think about it again. We consider the high to low transition, which means we start with the output at VDD and we go to VDD over 2 in the midpoint. Now, I want to look at the diffusion capacitance of my PMOS device. Okay, where's the diode? The diode is between this well, which is at VDD, and the output node. That's where this diode sits. So when the output is equal to VDD, what is the voltage over the diode at that period of time? 0, right? The voltage is VDD, this is at VDD, the well is at VDD. So we're basically in this point here. And then this is going to start to discharge. We see that we're going to get, the diode is going to get more and more reverse biased. So it's going to go to VDD over 2. So these are the extreme points. For the PMOS device, we're going to start with VDD, with 0 voltage over the diode, and the maximum value in the midpoint is VDD over 2. Okay? And that's the way we compute K equivalent for the PMOS for the high to low transition. Now let's think for the NMOS, the diffusion cap of the NMOS at this point in time. Here, the substrate of this device is at ground. So, where do we start? Well, in the initial point, you will see that this diode here, the diode from the drain to the substrate, the output node is at VDD to start with. The substrate at 0, so what's the voltage over the diode? It's VDD, reverse bias. So we're in this point. And then we're going to start discharging the capacitance. We're going to this point in the middle here. And again, we can find a K equivalent value for this particular interval. So what you see is that in the high to low transition, the diffusion capacity of the PMOS is going to be a lot more important than the one of the NMOS. Because here we are in the high capacitive interval. For the NMOS, we're in the low capacitive interval. So that is for the high to low transition. Now, if I want to do the low to high transition, it's just going to be opposite. Right? Because we start at 0, we go to VDD over 2. So the NMOS is going to be in that high capacitive interval, while the PMOS is going to move in this interval here. So the question really, to answer your answer, what is the extreme point? You have to look at the transition we're looking at. Is it high to low? Is it low to high? What's the begin point of the diode voltage? What's the midpoint of the diode voltage? You plug it in, you get your K equivalent factors. The nice thing, however, is once you've done this for your technology, if you know your supply voltages, and you know the value of the phi's and all these kind of things, once you computed your K equivalent, you can keep it forever. There's 90 nanometer technology. I compute the K equivalent, store it in my computer, and we're done. We know we don't have to recompute it again because it's always the same. As long as I don't change the supply voltage, because then, obviously, the in and end points are going to change. Okay? Is that clear? Yes.
When calculating C load,
Right.
so you lump together all the capacitance.
That's right.
But there is one from the V out to the VDD, right?
There's there's a bunch of them, right? But it doesn't matter, right? So you lump all your capacitance. So what do I get here? Well, I have my drain to my drain to bulk. I have my drain to bulk from the PMOS. That's C.
That capacitance you just drew on the top.
Yeah.
Why can you call that ground even though you're not using small signal?
Doesn't matter. It's a capacitance to DC. It's still going to give you the same charge displacement. Anything which is from a capacitor, when I charge it up and I look at the equivalent capacitance, I really figure out how much charge do I have to supply. If this thing is fixed, it doesn't really matter what voltage it's at. As long as it's a fixed voltage, I'm going to have to provide a certain charge to move the voltage across. All right? So as long as it's DC, you don't worry about it. You can actually lump a multi-capacitance to ground. Think about it for a second. See, it doesn't matter. It's not going to change anything. If I now put this capacitor to VDD or to ground, same exact result. Okay? It's only when you have a capacitor that's floating, where the input, where the node, both nodes change, then we have a problem. That's like this capacitor here, which we call the Miller capacitance. That's a nasty one. It's a floating capacitance, and you move one node in one direction, the other one goes the other way. And that's another story. In order to turn that into capacitance to ground, you have to use this Miller equivalent type of equation. Okay? Good. I think I worked myself to this list of questions. Any other questions that popped up in the meantime? Pretty clear? Good, so let's do a brief shot at some of those midterms. I have about 20 minutes, 10, 15 minutes, so let's see what we can do in that period of time. Now, don't be worried that some of the midterms might have questions you cannot answer. There might be a material that we haven't covered yet. It depends on very often how the material is covered in a particular exam. This is an exam from the spring of 2003 that we kind of look at. And so what we show in this particular case is a pass transistor network with various values of the inputs. And we have a certain on resistance. We assume that's an ideal transistor with a VT equal to 0.5, no leakage in the device, and we have given some capacitive values. Okay? And we assume that all input signals, A1, A2, B1, B2, C, and all those type of things, go between 0 and 2 volts. So capital T is equal to 1 microsecond. So you switch as 1 microsecond here. That's the capital T that's basically used in this equation here. Okay? So question 1 is draw the waveforms on nodes X and Y. Assume that all input signals are switching between 0 and 2 volts. There's 2 tricks in this question. The tricks really have to do with something that we discussed last lecture briefly, but something we've done already in the homework as well earlier on. It says, if I use an NMOS transistor to charge something up, okay, we know that if you apply a step, let's say we first put B1 from 0 to 2 volts, let's say, at time t equal 4. Right? So B1 goes on. node X is initially still at 0. Okay, nothing happens till T4. Now turning B1 on is not going to change anything unless, so this is 0, this is now equal at 2 volt, this is, we turn on the transistor, but still this is going to be equal to 0. So this stays at 0, or it's only when we start moving node A1 at times T/2 that this node is going to start to go up as well. The key challenge is how high does it go, right? And that's something we discussed last lecture, as I said, was in homework. When you use an NMOS transistor and I apply 2 volts here and I apply 2 volts here, the maximum voltage that I'm going to get here is what? It's not going to go all the way to 2 volts, but it's going to go to 2 volts minus VT, which is 1.5 volt. So what we're going to see is that node X is going to go up to 1.5 volts, okay, and not to 2 volts. That's really what this question was a little bit after, is looking at the impact of those threshold losses. Because then, for instance, when I turn on node C, oh, sorry, that's at time T/2. When I turn on C, so this is going to go like this, it goes up here, X is going to stay like that. So if you look at the Y output, so this is now going to 1.5 volt. C at times T/2 goes also on to 2 volts. So what's the value I'm going to get here? I'm going to get another threshold loss? The answer is no, right? Because see this signal here, the VGS, this is perfectly capable of charging this node all the way up to 1.5 volt. Once it gets to 1.5 volt, the VGS drops below VT and the node shuts off. But this can go all the way very nicely to 1.5 volt. So we're going to see at times T2 that this node is also going to go to the 1.5 volt. And that's really the whole crux of this story. Then we basically turn the nodes back off, they go back to 0. But first question, part 1 of this question was just to realize what's happening with the internal voltages from a DC perspective. Okay? So the second question is calculate the dynamic power dissipation of the circuit. I'm not too worried too much about this for this exam because dynamic power dissipation is something we are, well, you should know about CL/VDD squared, but we're not going to discuss, we have the dynamic power dissipation of an inverter is not something we have considered as part of the material for this midterm. So, but what you would do in this case is you look at every node in the network, node X and Y, and you figure out how often do they basically change from 0 to high voltage. We know exactly if it's going from 0 to VDD minus VT. What do you get as the power dissipation? It's CL times VDD minus VT. Remember that? There you have the factor that you have this power dissipation is not CL VDD squared, but CL times VDD times V swing. So the swing is not going all the way to maximum voltage here. That's why you have 2 volts times 1.5 volts. But let's stay away from, and the rest of the questions are also basically on power dissipation. So let's ignore those for the time being. Okay, this question is kind of a little bit more relevant. This is a question where we have two gates in series with each other. It doesn't matter if this is an AND gate or a NOR gate, doesn't play. It's perfectly legit in terms of the coverage of this thing. It's just looking at certain interesting questions to be answered. So this is an inverter. One of the other types of inverters not using an NMOS, but uses a PMOS, which is grounded as the load device. Okay? This inverter we call a pseudo NMOS inverter. Don't ask me why, I won't explain it right now. But it's called a pseudo NMOS inverter. Okay? What this PMOS does is almost acts like a current source. That's really what it is. It's like your resistive load with an NMOS. It's very similar in concept. Right? It's a load device that sits there, but this is the driver device. When this is low, device is off, this node will pull your output high. When the node is high, on the other hand, this transistor is on, we get a resistive divider. Right? Because this is a kind of a load device, it's just like we have in this case. When this device is on, the output is going to be equal to a resistive divider. And I made life easy for you in this question. It says, okay, I say, well, don't worry too much about the transistor. Let's assume that they just can be replaced by resistors. So the NMOS has a resistance of 10 kilo ohm. The PMOS has a resistance of 20 kilo ohm when it's on, linearized. So, hey, life becomes a lot easier. Okay, that's for a minimum size device. Okay, so question 1, assume that the PMOS is of minimum size. Okay, so that's good because we know that this can be now replaced by resistors of 20 kilo ohm. Okay, determine the sizes of the two NMOS transistors, MA and MB, so that VOL of the NOR gate, and I told you that it's a NOR gate, doesn't really matter, is at most 0.5 volt. Okay, so question here is, can you size me the transistor in such a way that this node, the VOL, is going to be at 0.5 volt max? Now, why is the max part here? Well, obviously, if you look at this, these are two resistors in parallel. Right? If I turn only one on, I'm going to have transistor, let's say I turn only transistor MA, I've got a resistor that pulls it down. Let's call this RA. And this is RC. Okay? If I turn both A and B on simultaneously, what I'm going to get is this. Right? You have two resistors in parallel. Now, which case do you think is going to produce the highest output voltage? What's happening when I put two resistors in parallel? What happens with the overall resistance? It goes down, right? That's right. The first case is the worst case condition. Because I put another resistor in parallel, this resistor becomes small, and this is a resistive divider. We know that the output the output is going to be equal to RA plus RB plus RC times VDD. Right? It's a resistive divider. So we can see that if B is equal to 0, I turn it off, you get RA over RA plus RL, which is worse than RA plus RB plus RA plus RB times RL. Sorry, I even wrong with that. This is parallel. Right? They have to be parallel. So I get smaller resistances, my output is going to go down. Okay? So worst case condition is forget about this guy, we're going to just size 1. Now life is easy because I know the supply voltage is 2.5 volts. We know that RC is going to be equal to 20 kilo ohm. So you have 20 kilo ohm plus RA times RA, and you set is equal to 0.5 volts. Out of that, I can solve RA right away. I can tell you what the value of RA should be to get 0.5 volts max. And that you can divide them to, and you figure out the size of the NMOS transistors. So it's just realizing that this is a resistor divider. You have a certain output voltage. What is the worst case condition? Fill in the equations, and you find the size of the transistor. Okay? Good. Now, next thing is I give you this table with a bunch of capacitors. Okay? Here's all those capacitors. I give you CGS, CGD, CGB, CSB, CDB. For W over L equal to 1. Remember that? When you size a transistor up, obviously you're going to have to multiply your capacitances with the size factor of your transistors. So the capacitors are going to size up. That's true for the NMOS devices. Determine the equivalent load capacity at the output of the NOR gate for A switching from A to 0, 0 to 1, and B equal to 0. And then both switching from 0 to 1. So what we have here is the following thing. Right? You have your PMOS grounded. So it's a trick. The trick here is just say, what capacitances should I really include in my analysis? Okay. So let's look at the case where B is fixed at 0. It's off. And we move A from 0 to 1. Okay, so what's going to happen with my capacitor? What capacitance do I have to take into account? First of all, if you look at the PMOS transistor, what's the PMOS going to provide? PMOS is going to add me a capacitance from drain to bulk, so the CdB of the PMOS. Any other capacitance I should consider of the PMOS in this case? That's correct. You have a other capacitance that sits here, the drain to gate capacitance. It's not a Miller capacitance in this case because the other side of the capacitor is fixed at ground. So I have to add basically the C gate to drain of your transistor, which in this case for the PMOS is 0.17. And it's a minimum size device, so we know the value. Okay? All right, and that's about it, right? The other capacitor, this capacitor doesn't count. The gate to bulk capacitance doesn't count. So that's all the only two PMOS capacitors I have to take into account. Now let's look at the NMOS, and there it's a little bit trickier. I have two transistors here in parallel. Obviously, for both of them, I have to include the drain to bulk capacitance. Right? In both cases, I have drain to bulk sitting there. We linearize it. We have the value here. Drain to bulk, it's 0.3. And depending upon the size of the transistor, we have to multiply this a little bit upwards. What else could we get? Okay, we have the gate to drain capacitances. And this is where the difference between part A and part B of this question comes in. In one case, I switch one input. In the other case, I switch both inputs. For this device, this is fixed to 0. So you see that the gate to drain capacitance has no Miller effect because the gate of this PMOS device is fixed at 0. For this guy, we have to double the capacitance because Miller effect happens, right? The gate goes up, the drain goes down. While if both of them switching, if A and B switch at the same time, we're going to have Miller capacitance on both. That's the difference between the two parts of the question. That's all. What else is left is obviously the capacitance of the load device. There's an NMOS transistor here connecting only one NMOS. No PMOS in this case, like we would have in a traditional inverter. So we know the capacitance of this. This is the gate capacitance of the NMOS device. So you have C gate, the total gate capacitance of the NMOS device, which is equal to CGS plus CDB plus CGB plus CGD. You add them all together and say that's the load capacitance that's offered by this inverter, this NMOS transistor here. Okay? And now the last part is very easy. I say, okay, now you have the capacitor, you have the resistor, compute me the propagation delay. It's R 0.69 times RC. So you're basically done. Right? Once you have the capacitor and the resistance, you're basically finished. Okay, so the last part of this thing is another question which you should not be able to answer yet. So don't worry about it. It's sizing of inverters. Okay, so let me get 5 more minutes to look briefly at this exam from the fall of 2005. This is an interesting one. Definitely worth considering and studying. It's where you have a very weird gate. A gate that is kind of bizarre. In the sense it consists of an NMOS transistor with its gate always at VDD, and then a bizarre load network consisting of a diode and a resistor. Okay? And the diode is, the characteristic of the diode is given when the voltage is smaller than 0.5 volt, there's no current through it. And when the voltage is larger than 0.5 volt, basically this thing is conducting and you have a fixed voltage drop of 0.5 volt over the diode. So the interesting first part, that's really where, if you understand this part, you're almost done with this question. Okay? is draw me the voltage transfer characteristic of this guy. Now, the definition of voltage transfer characteristic is V in versus V out, right? So let's think about this for a second here. This is nonlinear. Very nonlinear network. And diodes are really, really painful elements. Diodes, I can really make very tough questions with diodes. Because if you make the wrong assumptions, you can add all kind of bizarre type things. You can get very bizarre results. So how do you deal with nonlinear networks? That's kind of a rule that comes back all the time, over and over and over again. What do? You don't know what operational region they're in. Are they off or on? So what you do is you look at it for a while, you sit back and say, I'm going to make an assumption. I look at it, I'm smart enough, I'm just going to make an assumption. I say, let's assume that the diode is going to be on. And then you say, okay, the diode, when the diode is on, this is a fixed supply voltage of 0.5 volts. Then I can solve this thing, because the nonlinear part is gone. Okay? You solve the thing, and then you might end up with something that looks totally nonsensical. If it doesn't make sense, you probably made the wrong assumption. Go back and say, okay, wait a second here. I made the wrong assumption. Maybe the diode is off. Okay? That's the way you deal with nonlinear networks. You make an assumption, you find the operational region, and you solve the network for that operational region, and then you reflect on the result that you get. And the reflection says, well, the voltage that I'm getting at the output is higher than the supply voltage. You know you're going to have a problem. If you have something that's like minus 10,000 volts, you know you have a problem. Right? So that's what you should do in this case. So think about, for a second here, I apply an input of 0 here. The gate, this is a very simple NMOS device. We have the current, VT is 0.5 volt. We have a VT sat. We have gamma equal to 0, lambda equal to 0, ta-da. Not that hard. Okay. If you make the input 0 here, what do you think is going to happen with this diode at the outputs during that time? So basically at this point here, V in equal to 0. What do you think is the diode is going to be in? Just kind of rough sense. It's going to be off, right? I personally cannot see any way that diode can be on. You have to have that 0.5 volt from somewhere. So what's going to happen is my input is on. This thing is this is 0. The diode is off. So we're just going to couple the input to the output, right? This device is on. So this node is going to be equal to this node. So we keep on raising V in. V out is just going to be equal to V in initially. They're just going to follow each other. Then, suddenly this becomes equal to 0.5 volts. Now we have a different story. Because now suddenly this diode is going to turn on. We have the diode basically is active. And we're going to have now an equivalent network where you have something like this. That's V in, that's V out, that is VDD. And this is R. Now we can see that current is going to start to flow through this network. The diode is on, and we're going to have a current flow. So we know that the output is going to be equal, if this is I, we know that V out is going to be I times R plus 0.5 volts. Okay? Now we have to figure out what I is, but we can figure that out because we can write down the current equations for this network as a function of V in. And you plot it out, and you will see that suddenly this thing will change in slope. It will still go up, right? Because you have 0.5 volt, and you have this voltage drop of your current over this resistor. So this will keep on rising, but at a different slope than what it initially did. Now the question is, how far will it go? Will it keep on going up forever? Well, once I reach here, remember this is the good old trick again. If this thing is 2 volt and this is 2 volt, what's the maximum voltage you can get here? 1.5 volt. Actually, this thing is going to flatten out at 1.5 volt. And bingo, you have the whole thing. Yes?
What about the capacitor?
Capacitor doesn't matter. This is a voltage transfer characteristic. So it's a static characteristic. I'm not looking at transients. I apply an input voltage, and I can wait long enough, the output voltage will appear. The capacitor is only necessary for part number 2, where we say compute the propagation delay of this network. And when the input from 0 to VDD, let Vm and so on and so forth. So there's some assumptions here. But in the DC characteristic, when I look at voltage transfer characteristics, I'm never going to take capacitors into account. Okay. So I would definitely recommend that you take a shot at part 2 here, this propagation delay. Yes. That's your current. That's exactly right. So this is going to go and flatten out exactly at 1.5 volt. And you will see as a result of that you're totally right. The current is not a constant. You will see kind of a shape of this format here. Because the I is going to be determined, the I of this device is going to be equal to VGS. Yeah, you have to look at the operational mode of your transistor here. But it's going to be equal to VDD minus V out. And if it's a long channel device, or what, I think it's a long channel device. No, it's a short channel device. So we can use the VD sat times VD out my VN Kn prime type of equation. So you can see that your current is going to be a function of the output voltage. That's really what you're pointing to. Right? That is correct. That is correct. The VGS, but the VGS is right here. Right? It's here. The source is the lowest voltage of the transistor. So the VGS actually, that's why the transistor is going to shut off. Once the output gets at 1.5 volt, you have to have the VGS is going to drop below VT. The NMOS device shuts off, and we basically get a flat type of response. Yes? The question is, yes, that's a good question if this thing now would drop all the way down back to 0, which is one option. Right? You can say, okay, the transistor shuts off, we have no current flowing anymore. This thing is going to go shut all the way down because it's going to pull it down all the way down to 0. That's one option. It really depends upon how, we assume here that the leakage current to the device is 0. Yeah, if you would look at reality, that's exactly what would happen here. But no, actually it cannot. Right? If this device is at VDD, and this is at VDD, this node here, from the time you go a little bit below VGS minus VT, this node transistor turns back on. So it's going to keep it at 1.5 volts. It's going to clamp it. It's like something that clamps this thing all the way to 1.5 volt. You pull it a little bit lower than that, it's going to pull it back up. So it is staying at 1.5 volts. Okay? So, but it's an interesting thought process.